In the Aharonov Distinguished Lecture Series this evening. Named Professor Yegor Aharonov, who is internationally acclaimed pioneer in quantum theory and Mason's Distinguished Professor of Quantum Information Sciences. This lecture series brings notable distinguished laureates and renowned popular science writers to Northern Virginia and to George Mason University to communicate the relevance of quantum studies to the public. I would now like to introduce Dr. Jeffrey Tollefson, who is the Director of Mason Center for Quantum Studies, and who will introduce our great speaker tonight.
Thank you, Vikas. So, it's my pleasure and honor to introduce the eminent mathematical physicist, Sir Roger Penrose, who is here at George Mason for the first time. Professor Penrose is a professor emeritus at Oxford University. Tonight he's going to give a talk called Before the Big Bang, a novel resolution of a profound cosmological puzzle. Roger is probably best known for his work in cosmology and general relativity. He's gotten a huge number of prizes. I'll just mention a couple. With Stephen Hawking, he received the Eddington Medal and the Wolf Prize. He was honored with the Dirac Medal. He received the Einstein Medal, the Naylor Prize, and the De Morgan Medal. And in 1994, he was knighted for his many contributions to science. He's written 8 popular books, including The Laws of Physics, The Nature of Human Consciousness, etc. In his most recent book, The Road to Reality, A Complete Guide to the Laws of the Universe, sounds a little bit like the Hitchhiker's Guide to the Galaxy. But in fact, Roger has the real stuff in it. So, in today's lecture, Roger is going to give us a talk about the state of the universe as opposed to the state of the union. And particularly to be focusing on the early universe. So please join me in welcoming Sir Roger Penrose.
I hope you can hear me. If anybody can't, it's the usual thing. If you can't hear me, tell me. But it seems okay. It's a great pleasure for me to be here, and particularly to pay my respects to Yegor Aharonov, who I've known for over 40 years, I think. I should say that aloud. That's a great thing. No, he who is, of course, as we know here, achieved many great things in quantum mechanics, and not just understandings, but amazing things that we just wouldn't have expected. So I owe a lot to him. There'll be a little of quantum mechanics in this talk, but it mostly won't be about quantum mechanics. In fact, the profound cosmological mystery for which the nature... Now let's see, I have to make sure I get this the right way around. Here we are. Before the Big Bang, now about 2.5 years ago, if anybody had asked me, and they sometimes did, what happened before the Big Bang, I would have given the conventional answer. And the conventional answer is the Big Bang was a singularity in space-time, and therefore the notion of space and of time ceases to make any sense at that place, and so the very notion of before doesn't make any sense, and therefore it's a meaningless question. Now, I had a thought a little over 2 years ago, which sort of converted itself gradually into the sort of thing I'm going to be talking about here. It's an idea which is perhaps crazy. Of course, that's not such a bad thing necessarily. Is it crazy? Yes. But, well, there are various things that relate to it. I'll just sort of put them up here. I'm going to talk about some of them. I won't have time, presumably, to address all of them, but these are issues which are important in cosmology and physics generally. The first one being the second law of thermodynamics, which has a very particular character when you look at it on an overall scale, and I'll come to that. There are other things. There's something referred to as dark energy. I prefer to call it a cosmological constant. That's because I'm an old-fashioned cosmologist who used to read cosmology books in the old days, and every single cosmology book I'm aware of, at least before the last few years, talks about the cosmological constant. I'll say a bit more about that later. As soon as it was discovered to have a value other than zero, its name changed into dark energy. I'll come back to these matters later. It's not to be confused with something else, which is called dark matter. Dark matter also features in what I want to say, and there are other topics, like the nature of the cosmic microwave background, the black hole evaporation paradox, information paradox, and things about mass and whether it is absolutely constant or not. Now, I'm not going to talk about all these things. I'm certainly going to talk about the first topic primarily, and the next two. These are things, whether the theory, the scheme I'm going to describe, actually explains these things is another question perhaps, but what it does is require them. So if these things weren't as they are, you would have, this theory would not work. It may not work also for various technical reasons, but those are things that we don't know yet. So I'll have to say a bit more about all this. But to begin with, let me say, I think I'll put this on the other side probably, and just leave that there. Put the crazy out of the way. I should explain that crazy is not a derogatory term. It's probably almost a necessity for any advance in fundamental areas in physics. So we shouldn't regard it as a bad thing, particularly because there are lots of other crazy ideas which physicists have put forward, also which refer to something going on before the Big Bang. I should start by talking about, in 1922, the Russian mathematical physicist Friedman introduced, well, he provided the first solutions of the Einstein field equations in a cosmological context. The first cosmological models in accordance with Einstein's theory. And in one of these, K equals to naught, I'll explain what that means in a minute. In one of these, the universe, well, you see here we have the radius of the universe upwards and time going along horizontally. And the idea, well, this curve is what's called a cycloid. It's described by a circle and a plane rolling along that line, and a point on its circumference traces out the cycloid. And you notice that this curve just keeps on going. Of course, the radius here starts with 0, goes up, and then comes back down to 0 again. You might think that that's the end of it. That's usually, these days, we call that the Big Bang, and this the Big Crunch. But since it's a cycloid, it was a great temptation for people to think that the universe kept on going. In fact, it always used to be referred to as the oscillating model of the universe. There are modifications of this, because people sometimes worry a little about the second law of thermodynamics. The second law tells us that a thing called entropy is increasing as time goes on. I'll come back to that in more detail in a moment. And the American mathematician Coleman took this seriously and had a model in which it's a bit like this model, but the cycles kept on increasing, and you did have entropy increasing in a certain way. So it's starting to take into consideration the problems of the second law of thermodynamics, but as we'll be seeing, it's only an extremely mild way, and you needed a lot more than that. I think it's all been, I have to move it forward, probably. If I move it backwards, then you will see less of this. If I move it forwards, I'll run into this thing here, so I think I'm stuck. So, I'm sorry about that, but I think it's reasonable. I'll try not to get it overflowing at the edges.